Today, we will talk about the altimeter. The altimeter is one of the basic flight instruments, and it is connected to the pitot static system, which we discussed in a previous video. Here we have a simple schematic of a typical pitot static system. As we can see, the altimeter is connected only to the static port, which means that it receives static pressure information only. Now, before continuing, we should mention that there are different types of altimeters depending on their principle of operation. First of all, we have the barometric altimeter. This type of altimeter, as its name implies, uses barometric pressure to give its reading. Then we have the radio altimeter or radar altimeter, which uses radio waves to measure the height in relation to the surface. And finally, there's the GPS or GNSS altimeter, which uses satellite-derived geometrical data to determine the altitude. In this particular video, we will focus on the barometric altimeter, as it is the one used in most air operations and can be found in all aircraft. So let's see exactly what a barometric altimeter is. In simple terms, this is an instrument that measures the vertical distance between the aircraft and a specified reference level. This reference level will be the one at which the altimeter will indicate 0. And therefore, the altimeter will measure how high the aircraft is with respect to that level. This vertical distance can be expressed in terms of feet or meters, even though most altimeters are calibrated in feet. At this point we might be wondering, why do we say vertical distance instead of altitude or height? Well, that is because that vertical distance may have different names depending on the reference level we are using. Let's see an example of this. If we measure the vertical distance between the mean sea level and the aircraft in flight, we will be measuring altitude. If we measure the vertical distance between a point on the ground and the aircraft in flight, we will be measuring height. And if we measure the vertical distance between the mean sea level and a point on the ground, we will be measuring elevation. Now, the term flight level is also used to refer to a certain vertical distance, however we will deal with that concept later. So far, we will only be using these three concepts of altitude, height, and elevation. With this being said, let's now focus on how does a barometric altimeter actually work. As previously mentioned, this type of altimeter uses static pressure, or in other words, atmospheric pressure to determine altitude. It takes advantage of the fact that the static pressure decreases with altitude. Therefore, if we measure the pressure at low altitudes, it will be higher than the pressure at higher altitudes. This means that, if the altimeter senses a high static pressure, it will interpret that the aircraft is flying at a low altitude. And in the same way, if it senses a low static pressure, it will interpret that the aircraft is flying at a high altitude. So in other words, the barometric altimeter interprets pressure changes as altitude changes. That's the reason why the altimeter needs to be connected to the static port, since it needs to detect changes in atmospheric pressure to give the altitude reading. Now, by default, the altimeter is calibrated to measure the altitude in relation to the mean sea level under standard conditions. As we mentioned in the video about standard conditions ISA, the standard pressure at sea level is 2992 inches of mercury, or 1013 hectopascals. In this video, we will use inches of mercury in the examples, however the concept is the same for hectopascals. In this case, if the altimeter senses a static pressure of exactly 2992 inches of mercury, it will read 0 feet, since it is the barometric reference level. Now, if the aircraft starts to climb, the static pressure will decrease, and therefore the altimeter will show an increase in altitude. Let's suppose, for example, that this aircraft climbs up to a point where the static pressure is 2514 inches of mercury. In this case, what the altimeter does is compare the new static pressure value with the reference pressure of 2992 inches of mercury. And based on the resulting pressure difference, the altimeter can calculate the altitude above the reference level. Having understood this basic principle, let's see what actually happens inside the instrument case. As we know, the instrument is connected to the static port, which fills the instrument case with static pressure. Now, inside the instrument there's an aneroid capsule, which is sealed with a constant pressure inside of 2992 inches of mercury, which, as we previously mentioned, is the standard reference pressure. This capsule is connected to gears that move the needles on the instrument dial. In this case, if the aircraft is at sea level, the static pressure inside the case will be roughly equal to the pressure inside the aneroid capsule. In this situation, the aneroid capsule will be contracted and the needles will indicate 0 feet. Now, if the aircraft starts climbing, the static pressure inside the case will gradually reduce. And since the pressure inside the capsule remains the same, the pressure differential will cause the capsule to expand, moving the gears, which in turn move the needles of the altimeter to indicate an increase in altitude. On the other hand, if the aircraft starts descending, the static pressure will gradually increase, causing the aneroid capsule to contract again, moving the gears and needles to indicate a lower altitude. So far, we have used 2992 as the reference pressure at sea level. This pressure is known as the barometric reference, which, as we previously said, is the pressure level at which the altimeter would indicate 0 feet. And all indications will refer to the altitude of the aircraft in relation to this level. By default, this barometric reference is 2992 inches of mercury, just because it's the standard sea level pressure. However, in practice, the pilot can actually change this barometric reference to any other value. But we might be wondering, why does the pilot need to change the barometric reference? Well, let's look at it by means of an example. As we already know, the actual altitude is the vertical distance between the mean sea level and the aircraft. And under standard conditions, the pressure level that identifies the mean sea level is 2992 inches of mercury. From this point, the static pressure decreases with altitude at a rate of approximately 1 inch per 1,000 feet. And theoretically, below the mean sea level, the static pressure would increase at the same rate. Each of these lines that identify a pressure level is called an isobar, and they will be very important for this explanation. Here, under standard conditions, as our altimeter is calibrated by default to use 2992 as barometric reference, it will indicate the vertical distance between the 2992 isobar and the aircraft. And as the 2992 isobar and the mean sea level are in the same position, the indicated altitude will be the same as the actual altitude. The thing is that, in reality, we almost never have standard pressure conditions, so in other words, the 2992 isobar almost never identify the mean sea level. Let's look at two different scenarios, one with a higher than standard pressure and the other with a lower than standard pressure. Let's begin with the higher than standard pressure case. Here, the isobars will move upwards, causing the 2992 isobar to no longer represent the mean sea level. Now, the new pressure level that identifies the mean sea level is the 3040 inches of mercury isobar. In this situation, if our altimeter is still adjusted to use 2992 as barometric reference, the indicated altitude will be lower than the actual altitude. This happens because the instrument is measuring the altitude in relation to the 2992 isobar, which in this case is higher than the mean sea level. The solution here is to readjust the altimeter to use 3040 as the new barometric reference, since it's the current pressure level that identifies the mean sea level. This way the altimeter will measure the actual altitude correctly. The current level pressure that identifies the mean sea level in a certain moment is known as QNH, and it will vary depending on the atmospheric pressure changes. It is therefore important that the pilot receives updated QNH information at regular intervals while flying in order to adjust the altimeter to indicate the actual altitude precisely. Let's have a look now to a lower than standard pressure condition. In this situation, the isobars will now move downwards, causing the 2992 isobar to no longer represent the mean sea level. In this case, the new pressure level that identifies the mean sea level is the 2970 isobar. In other words, the QNH is now 2970 inches of mercury. So if in this situation the altimeter is adjusted with 2992, the indicated altitude will be higher than the actual altitude. Therefore, in order to obtain a correct altitude reading, the pilot will have to adjust 2970 as the new barometric reference, since it's the new pressure level that identifies the mean sea level. So far, we have seen examples where we adjust the altimeter to get a correct altitude reading. But what if we want to measure the height in relation to the terrain instead of the altitude in relation to mean sea level? Well, in this case, the pilot can adjust the altimeter to use the ground level as reference. First, let's refresh some concepts. As we mentioned, the vertical distance between the mean sea level and a point on the ground is known as elevation. And under standard conditions, we would have the isobars distributed as follows. So how should the pilot adjust the altimeter to indicate the height above the airport? In this particular case, the airport elevation is 2,000 feet, and as we can see, the pressure level that identifies 2,000 feet is 2792. So in order to indicate height above that airport, the altimeter must be set to use 2792 as barometric reference. In this situation, as we are no longer using the sea level pressure as a reference, the value used to adjust the altimeter is no longer the QNH. It is now the pressure at the airport level, which is known as QFE. Now, as with the QNH, if the pressure conditions are different from the standard, the QFE for a certain airport will vary. Therefore, it is important to obtain updated QFE information if we want to use heights instead of altitudes in our altimeter. You might be wondering by now, how can the pilot adjust a certain barometric reference in the altimeter? Well, that is performed through the Colesman window. This is a little window in the instrument dial which allow the pilot to change the barometric reference using the knob labeled as Baro Adjust in the bottom left corner. The Colesman window is calibrated either in inches of mercury or hectopascals. There are even instruments that include both pressure scales. So to summarize, if we adjust the QNH as barometric reference, the altimeter will indicate the altitude above mean sea level. While if we adjust the QFE as barometric reference, the altimeter will indicate the height above the airport. It is therefore logical that if we adjust the QFE of the airport while on the ground, the altimeter should indicate 0 feet. Now that we have seen how the altimeter works, let's see how the needles of the instrument are interpreted. First of all, let's see which are the different needles we will find in the dial. There is the triangular needle, which indicates tens of thousands of feet. So if this needle points the number 1, it represents 10,000 feet. If it points number 2, it represents 20,000 feet and so on. Then, there is the short needle, which indicates thousands of feet. So if this needle points the number 1, it represents 1,000 feet. If it points number 2, it represents 2,000 feet, and so on. Finally, there is the long needle, which indicates hundreds of feet. So if this needle points number 1, it represents 100 feet. If it points number 2, it represents 200 feet and so on. Let's see some examples of how to read the altimeter using the 3 needles together. In this case, all 3 needles are pointing 0, which indicates 0 feet. So in other words, the aircraft is exactly at the barometric reference level. Now let's suppose the aircraft climbs and the altimeter shows this indication. In this case, the triangular needle is between 0 and 1, therefore it indicates that the aircraft is between 0 and 10,000 feet. Then, the short needle is between 1 and 2, which means that the aircraft is above 1,000 but below 2,000 feet. And finally, the long needle is pointing number 4, which represents 400 feet. So with this, the altimeter reading is 1,400 feet. In this other situation, the triangular needle is between 0 and 1, the short needle is between 7 and 8, and the long needle points number 5. So the altimeter reads 7,500 feet. And in this last situation, the triangular needle is between 1 and 2, which indicates an altitude above 10,000 but below 20,000 feet. The short needle points number 2, which indicates 2,000 feet. And the long needle points 0. This altimeter is then indicating 12,000 feet. Now, the use of this 3-needle system results in a little problem. If we observe these 2 altimeters, we can see that the short and long needles are in the same position. However, the altimeter on the left is indicating 2,000 feet, while the one on the right is indicating 12,000 feet. So the only way to notice the difference is by looking at the triangular needle, which sometimes can be difficult to see, especially under high workloads. So it is likely that an unaware pilot may misinterpret the reading. This is the reason why most altimeters incorporate a 10,000 feet flag with black and white stripes. This flag is visible when flying below 10,000 feet, but it disappears when flying above this altitude. This way the pilot can easily determine if the aircraft is flying above or below 10,000 feet. The other thing to take into account is that each altimeter has a certain maximum calibration altitude. Since some barometric altimeters are more sensitive and accurate than others, each altimeter is certified to measure the altitude correctly up to a certain level. In this particular example, we can read in the dial that this altimeter is calibrated up to 20,000 feet. So if the aircraft climbs above 20,000 feet, the altitude reading may have significant errors. This happens because as the pressure reduces with altitude, it is more difficult for the altimeter to sense correctly the changes in pressure and interpret them as changes in altitude. This is why some altimeter designs are more accurate than others. For example, there is the simple altimeter, which is widely used in small aircraft that fly at low altitudes. The sensitive altimeter incorporates a second aneroid capsule and a temperature compensation system, which increase the accuracy and performance at higher altitudes. And finally, the servo-assisted altimeter incorporates an electric motor that allows the instrument to measure the pressure changes with a much higher accuracy. Now, there are also different types of instrument presentations. Some altimeters replace two of its needles for a numeric altitude indication, as we can see in the picture. And some others are adapted and incorporated into digital presentations of the electronic flight instrument system. Now, we must bear in mind that the altimeters are not perfect. They present instrument errors related to wear of the gears and mechanical imperfections, as well as position errors caused by pressure measurement errors of the pitot static system due to maneuvers or changes in aircraft configuration. This is why the manufacturer publishes an altitude calibration table that allows the pilot to apply the corresponding altitude corrections in order to obtain the calibrated altitude. This table takes into account altitude, airspeed and aircraft configuration to show the corrected values. However, normally these are small corrections that do not exceed 50 feet. Now, as we can see, this altitude calibration table is designed to be used with the normal static source. But what happens if this static port gets blocked? Well, in this case, the altimeter reading will freeze. So, regardless of subsequent changes in altitude, the instrument needles will be frozen, indicating the altitude at which the static port got blocked. Let's see what actually happens inside the instrument in this situation. When the static port gets blocked, the static pressure inside the instrument case will be trapped, and therefore it will remain constant. This means that the aneroid capsule inside the instrument will not expand or contract, keeping the needles frozen. So, how can the pilot solve this situation? Well, in most aircraft there is an alternate static source, which can be activated from the cockpit using a switch. Now, in case of using this alternate source, the pilot must consult the corresponding altitude calibration table. Since, as we already know, the static pressure sensed by this alternate source is slightly different. Here we can see an example of an alternate static source altitude calibration table. As we can see, it is very similar to a regular altitude calibration table, so it is used the same way. I hope the information presented in this video has been useful. If so, don't forget to share, like, subscribe and leave a comment down below. Thanks for watching.